Yeah, I think the recording has just started. So, okay, hello everyone. Today we have Nimish from IIT Kharagpur, who is currently at third year PhD working with Devdeep. And he will be talking about his recent work that appeared at NDSS 24. So, over to you, Nimish.
Thank you, and thanks a lot for having me here. So I'll be talking about our work where we used system bus faults to attack armed trust zone. This work was presented at NDSS last year as well as at the Black Hat Asia Conference 2024. So essentially, the structure of this presentation is thus. We'll just cover briefly on how traditional architectural aspects of SOCs have been exploited from a fault injection point of view. So essentially, fault injection on processor and memory. Then I'll just briefly touch over how the system bus behaves, or rather links processor and memory from a SOC point of view, and why it's very lucrative from a fault injection perspective. And then I'll describe in detail on how we exploited the system bus faults to attack a commercial implementation on ARM Trust Zone, that's the Open Portable Trusted Execution Environment, or OPT, and what kind of interesting insights we had and how we essentially ended up in delivering a countermeasure for this as well. So to begin with, traditionally from my SOC perspective, so system on chip would be the focus of this entire presentation. So from a SOC perspective, traditionally the fault injection works have been focused mostly on either the processor or the memory. So processor faults can be broadly classified into two distinct types. So one could be where we assume the adversary has a physical access to the victim platform. So that can be an external interface through which a clock glitch can be inserted into the victim platform. So that's one example of faults that can be done on the processor. And second could be a much stronger assumption, that is the adversary is a remote adversary now. So DVFS, or dynamic voltage frequency scaling interfaces. So many of the high performance systems, they offer, even high performance SOCs, they offer a lot of interfaces which allow software to balance performance and energy consumption. So people figured out that using these interfaces, we can actually throttle the core, throttle a CPU to its limits, and there we have timing violations in the sequential circuitry of these CPUs. And these kind of fault attacks can be done remotely. And prior work has shown that these kind of fault attacks, they are very powerful and uh, very important in the context of trusted execution environments as well. On the memory side, again, we can have row hammer. So row hammer is again something that can be performed on a remote system, by which I mean the adversary does not need to have physical access to the victim platform. And then, of course, we can have physical fault injection as well. So we can have optical fault injections, or we can have electromagnetic fault injections. So here's a like very brief different umbrella terms, or rather umbrella classes of fault attacks which people have been trying to do on SOCs. And there have been differences as well. So for instance, in many of the recent SOCs like Raspberry Pi Model 3 or 4, or even now 5 is in the market, we usually do not have any interface which can allow an external device to manipulate the CPU clock. So those kind of glitch attacks can no longer work on these high performance SOCs. Essentially, they can still work on like resource constrained microcontrollers and FPGAs, for instance, but not on high performance SOCs. The remote attacks, the DVFS that I just mentioned, these interfaces have by design now been restricted for access from an unprivileged point of view. So if the adversary is not privileged, by which I mean if the adversary is in, let's say, the ring 3 of the operating system, then it cannot access these interfaces anymore. So DVFS kind of attacks are also no longer, or rather, if you have configured your system correctly, then DVFS kind of attacks can also no longer be uh, performed. On the memory side also, in Rowhammer, there have been suggestions to incorporate error correcting codes, which can detect and in some cases even correct Rowhammer faults as well. I agree that ECC checks in context of Rowhammer can be something which would be inhibitory to the memory performance, but we are just talking about whether there exists any defenses or not. So it is possible to defend against Rowhammer, although it's a bit expensive from a performance perspective. And against physical fault injections, we have casings now. So essentially, you can cover your memory chip with a casing. This does not stop an adversary from performing a fault injection. It additionally requires the adversary to first decase that particular casing and then perform the injection. So in some cases, it will not prevent a fault injection, but definitely it will make the injection detectable. So the owner of the platform will know when a particular device has been tampered with, and probably they can do something about it, essentially, like maybe change the device or something like that. So in this particular work, given all this context about processor faults and memory faults, our intuition was whether we can target any architectural aspect of SOCs which has not been targeted so far, and for which we do not know of any defenses yet from a fault injection perspective. And that's when we ended up at the or ended up thinking about the system bus. So the system bus is an architectural aspect that connects the processor and the memory. So the processor and the memory, they sit as separate chips on the PCB, and the system bus would be responsible for bidirectional communication between them. And we thought that this could be a very nice point of injection, or even if it doesn't bear any fruitful results, it would be a very nice architectural aspect from a fault injection point of view that we can explore. And the reason for that is because there have not been prior works, or up till last year, we could not come across many prior works which actually did practical fault injections on system buses. There were simulations though, but nothing concrete. So the system bus is uncased and it's exposed. So for instance, on the right hand side, we have the exposed bus connections, figure of that on Raspberry Pi 3 essentially. So the black chip you see, that's the memory chip. The processor sits on the other side. So the processor backside we have marked in yellow, and the connections you see on the PCB between the between the memory chip and the processor backside, that's marked in red. That's essentially the system bus sitting there. So it's uncased, it's exposed, and we can essentially put injection probe on top of this and potentially do something. Now, if we are targeting a system bus, the very first challenge we run into is, unlike processors, system buses are only concerned with two instructions. So they will only be concerned when the processor needs to interact with memory, by which I mean they'll only be concerned with load and store instructions. If you're working with the processor, then you have more options, but with buses you have just a couple of options. And this is where we thought it's a very good point to try and see what we can do with faulting these memory cycles, or by which I mean faulting these load and store instructions. So I'll just briefly summarize of what we came across. So assume the processor executes a load instruction. So the way it does that is it places the memory address onto the address bus, which is a subcomponent of the system bus. This address bus interfaces with the memory chip, and wherever this memory is located in the wherever this address is located in the memory chip, the data from that particular memory cell is put on the data bus, which is another component of the system bus, and it comes back to whatever destination register the processor is aiming at. So that's how a load instruction works. So we wrote a very simple code that executes a lot of load instructions, and we mounted the probe as in the diagram as well here. So essentially, we mounted the probe on the backside of mounted the probe on the backside of the Raspberry Pi 3 processor, and the idea is if we play around with the electric field in the loop that you see in the figure, so it's the electric field changes are in a plane parallel to the Raspberry Pi 3 processor, and they will cause magnetic field changes perpendicular to that. And by perpendicular, I mean the magnetic field changes will essentially be injected into the Raspberry Pi 3 PCB. And depending on where you place the probe, those magnetic field changes can affect different portions, different components of the PCB. In our case, they would be affecting the system bus itself. So here's how the load instruction will work. Uh, so we already talked a little bit about this. The processor will place the memory address onto the bus, which will go to the memory. The memory will return back the data. But the idea is while this transition is happening, if we inject the fault, by which I mean if we play around with the electric field in the loop, then the magnetic field changes perpendicular to this plane, should theoretically cause problems in the system bus itself. And the idea is to check whether that leads to any faulted data being loaded by the processor. And we were successful. So we tried out a full-fledged attack, a differential fault attack on AES. The idea was we begin with a table-based implementation. So the reason being, first of all, we don't have acceleration for AES on SOCs. And secondly, since we are doing bus faults, and it makes sense to use table-based implementations. So the tables are sitting in the memory, and we have several load instructions which are trying to load that data onto the processor. And at very specific points, like in round 8, for instance, when the load instructions of that round are executing, we inject a fault, by which I mean we change the magnetic field in this black loop that you see. So we change the electric field in the black loop that causes change in the magnetic field perpendicular to it. And we did observe that the ciphertext actually changed. So there is a bit flip here, if you see. Actually, two of the bits have changed. Yeah, so it's a double bit flip, I should say. And in one of the ciphertext that was at iteration 47, we did observe that the final ciphertext was much different from the actual value. So all the black ones you see, they are the correct ciphertext, and this red one is where we were able to inject a fault. And from there, we used post-processing techniques from Professor Devdeep only, and we were able to bring down the key entropy to the power 8. So this end-to-end, this was a dummy exercise that enabled us to understand how system bus faults work, and also enabled us to configure our entire hardware of fault injection to have precise faults in the operation for choosing, and to have an end-to-end attack on AES as a proof of concept that bus faults can actually work. So now with this information, it's a good point to compare these faults with faults in memory and bus. So when we talk about fault injection, the very first and probably the one of the most important things are the probe position. So where on the PCB are we placing the probe? So first of all, the probe position, or where exactly we chose to place the fault injection probe, it did not have any effect on memory. So that's kind of a physical layout of the PCB where we choose where exactly we place the probe. So that was different, first of all. And secondly, we also did other experiments to just have more sanity checks with this. So what we did was we executed many more load instructions after the fault was being injected. and we did observe that the fault was not persistent, by which I mean that if we remove the probe, then whatever data comes from memory, the data is correct. So the fault is indeed transient. The hope was that if we had accidentally injected a fault in the memory, then unless and until we refresh the process binary, by which I mean unless and until we create new stack frames for functions, the data in those stack frames will actually remain faulted, even for the load instructions which follow uh, follow the load instruction that was actually faulted. So if the 10th load was faulted, then if we had accidentally injected the fault in memory, then the 11th load would also have given the wrong value, because we ensure that the lifetime of the stack frame, the lifetime of that variable in memory, it far exceeded that than the duration of the fault injection. So we did a lot of sanity checks to make sure that we are not accidentally faulting the memory. And similarly, we did checks to make sure we are not accidentally faulting the processor. So again, probe position, that's one of the main differences. So we are not placing the probe over the processor, but we still did multiple experiments where we observed that if we actually place the probe on the processor, then the DFA on AES attack that I just mentioned was not reproducible. And the reason was that the platform we were using, it actually had metal casing over the processor. So it is expected to not work, and it was indeed not working. But if we shift the probe from the processor to focus on the system bus, then the attack was actually working. So both of these experiments, they gave us some confidence, a lot of confidence to be honest, that we are actually being able to localize the fault to the system bus and not on the memory and the processor. So we had something on our hands to go on with. So next comes the question of how well can we control it. So again, we return back to our example instruction, the load instruction. And so in some of the cases, we were able to fault the data that was loaded into the destination register. So the way to do that is very simply program the memory address to a fixed value like hexFS or any predetermined value, and just check what data is being loaded into the destination register. If it is the same, then that essentially is a no fault scenario mentioned here. If it's incorrect, then the fault was successful. And we further broke down the successful cases into two sub cases where we loaded data which were all zeros. So deliberately we programmed the memory such that the memory did not have all 0 bits, but the registers, all 32 bits of the registers were 0. So that is the case 35% here, that was fault to hex 0. And other cases, 27% here, they imply that the fault was successful. So we were able to change the loaded value from its initial value. However, it was not all zeros. And we also observed faults in the address bus as well, by which I mean the address itself was faulted so that the load was pointing to an address space outside the permissible limits of the process we were working with. So that is essentially a segmentation fault. So in some of the cases, we observed a segmentation fault. In most of the cases, we actually did not observe segmentation faults. So segmentation faults were lesser in frequency. The data faults were more in frequency from our empirical observation. These are all empirical observations. And I like to point out this particular case in particular because this is something we'll be using to attack the T as well. So we're calling it a register sweeping, by which I mean it cleans the value of a load. So it doesn't matter what the memory contains, the value of the load will always be 0 if this kind of fault is successful. And it turns out that we can use these kind of register sweeping faults to mount an end-to-end attack on the commercial T implementation on ARM trust zone. So I'll just explain how that works. So the architecture of Opti that we are working with is something like this. I'll just unpack it for you here. So Opti implements a split OS kind of architecture. the idea is two different kernels are sharing the same hardware. On the right hand side, the red boxes, that's where most of the applications will reside. It's a stripped down version of Linux. And we have at the very top, we have REE user space exception level 0. So REE is a rich execution environment. And the innocent CA mentioned here, that's a client application. So innocent as in we are at this point assuming this client application on the right hand side, it's not doing anything maliciously. The fault injection is external to the device. So we're not assuming any code execution on the normal world side at this point. Then you have kernel space exception level 1. So that's where some system called handlers stay. We just need to understand that control flow begins from the top right, and then through a series of function calls and system calls, it goes to the monitor layer at the very bottom. So that's the exception layer 2, which context switches to the left hand side, the green boxes, the secure world. That's completely different kernel that's running. And then again, through a series of system calls, we go from uh, the T kernel space to the T user space. And that is where a TA initiation is happening. So TA is short for a trusted application. So a TA initiation means some code is running in the trusted part. And then I've just given an example that this trusted application is actually using some APIs from crypto library like libtomcrypt as an example, and it's doing some crypto. We're not concerned with what it's doing at this point, but that's how the privileges are defined. So even the code that is running inside the TE is not doing crypto by itself. It is still relying on its own kernel APIs, and those APIs are doing the crypto on behalf of the TA. And once all this is done, control flow goes in completely reverse direction. So from kernel space exception level 1, this libtom crypt, the control flow will go back to EL0, the top layer. And from there, again, it comes down to exception layer 2 at the very bottom, and then it switches to the right hand side. So essentially, the exception level 2, which is the monitor, it controls context switches between the two worlds, the right hand side and the left hand side. And the idea is on the right hand side, anything that you do not want in your trust boundary should be executing. On the left hand side, the trusted applications should be executing. And there exist APIs for both of these worlds to communicate with each other. Now, we were mostly interested in this particular point, the TA initiation point, because this is the point where the code that executes on the left-hand side in the green box actually loads into the address space of the secure world. And here's a pseudocode of what exactly happens. So once a load TA function is called, it actually verifies its signature. And signature verification is asymmetric RSA. So if the signature is valid, then we return a T success macro. Otherwise, we return a T error security macro. And once control flow goes back to load TA, if a T success was returned by the verify signature, then essentially we execute that particular code. Otherwise, we panic. We induce a kernel panic on the secure world side. Now notice here that we have zeros and non-zero values here. So this immediately connects to that register sweeping fault that I just mentioned. So if we can have a register sweeping fault in this particular scenario, then doesn't matter what code we try to execute on the T side, even if its signature fails, which it will, because we are not authorized to run our own code on the T side. So when the signature fails, it returns a non-zero value from memory, that's true. But because of the fault, it becomes all zeros. And the moment it becomes all zeros, the if condition that you see in the load TA function, it passes, and rather I should say it's not equal to T6. So the if condition actually fails, and the code that the adversary is trying to execute in the secure world simply runs, giving the adversary arbitrary code execution on the T side. So that's the main idea of our attack. Now, a good question might be, why can't we do this attack through other methods of fault injection? So external glitch, DVFS, row hammer, in the platform of our evaluation, they were not working. So we discussed it a little bit in the previous slides. Now, one good point can be that why can't we forge signatures? So we have our own code and we forge its signature such that the signature verification passes. And the way of doing that would be using side channels to maybe steal the signing key, or not even side channels. Maybe we just use direct attacks like we have buffer overflows or other kind of attack vectors that lets us steal the signing key and then self sign our own code. But the problem is the way Opti architecture is defined. The signing key is actually not on the device, only the verification key is on the device. So there is absolutely no way for us to get the signing key as well because it's not on the device. So other kind of attack vectors really did not work out for us. So we went ahead with bus faults on this. And that's the main crux of our contribution, the first contribution essentially, that doesn't matter what code we are trying to execute on the secure world side, we can always make it execute if we are able to have a successful register sweeping fault. So that is because when the callee function, this second function here, when it tries to load the return code of the first function from the stack frame of the first function, the actual value is all this four Fs followed by triple zeros and another F. So it's a non-zero value essentially. But a successful register sweeping fault will give us all zeros, and that's what we want essentially. And you would recall from the previous slide that our success rate of a register sweeping fault was less than 50%. So that's not a very ideal success rate for a fault injection setup. But at the same time, we don't need many faults. The idea is once your code gets into the trusted world, it remains there. So it's like we need one successful fault. So that's why we could actually live with even a subpar success rate. So with that out of the picture now, the second question is, when do we know to inject, when do we know, or rather, when should we inject a fault? So in fault injection literature, as well as many experiments out there, the second part is mostly easy, which is the second image you see here. That's the actual fault injection. But the first part is related to a fault trigger. So something should trigger the entire fault injection hardware, and then the fault will be injected. So we need to precisely calibrate the trigger to align with the operations which we want to fault. Now, usually what people do is they have code-based triggers, by which I mean there's some code running on the platform and it sends a signal through a GPIO pin, and that drives the entire fault injection hardware and the fault is injected. But in our particular case, the code that is running is actually running at the monitor layer. So if I show you the architecture, this particular code that is running, it's running at the monitor layer. That's the highest privilege, even more privileged than both of the kernel spaces here. So we cannot have code triggers there unless and until we recompile the opti kernel, and that's outside the threat model completely. So we circumvented this problem by constructing a combined adversary. The idea is, not sure what's happening. Can you see my screen? I just
Yeah,
went
now
black.
it's back. Now it's back.
Okay, I'm not sure what happened. Just a second, let me
I
quickly
think there was a fault attack.
a
Anyway,
network
go
fault.
on.
Yeah. Yeah. So just to recap, the idea is we need a code, we need a fault trigger. but we cannot have code triggers here because otherwise we'll have to recompile the opti kernel, and that's outside the threat model. So we came up with the idea of constructing a combined adversary, and the idea is the adversary will have both side channel and fault injection privileges. So this idea has been explored a lot in fault injection literature in other contexts, maybe mostly in attacking crypto and all. But we thought that probably we can use side channels as a way to trigger fault injection, and that's what we essentially did. So we have a power side channel measurement device which is completely non-invasive, so no changes required to the platform or its code base. And when the signature verification starts, we drive the entire fault injection hardware, and that ends up essentially injecting the fault. So on the right hand side, we have the annotated oscilloscope output of the different components of fault injection hardware that's working. But the best takeaway from this particular annotated output would be this unavoidable latency that you see here. And that's why fault injection is a lot of it requires a lot of empirical work to perfectly align this unavoidable latency. So the very last signal that you see, that's the magenta signal, it needs to be aligned to the move instruction, essentially, the top level green signal. And this unavoidable latency is because of the propagation delays of different aspects of the hardware we are working with. And this is all empirical. So we just sit with the hardware, we keep on doing it again and again unless and until we hit a certain setting that is giving us favorable results. So using a combined adversary, a side channel to trigger the fault, and the fault injection itself, we were actually able to get our arbitrary code execution in ARM trust zone. So a self-signed adversarial control. We are calling it a self-signed because it doesn't matter what signature you provide. And you can provide an arbitrary signature as well. You can provide a signature with a wrong key as well. It will still execute in the trusted execution environment. So now the question is, we have code execution on the trusted side of Opti, but what can we do with it? Because even the TAs, they are isolated from each other. So one TA cannot actually see memory address spaces, cannot see communication of other TAs. There is no connection between the two TAs unless and until both the TAs decide to share memory. That's the best two TAs can do on the trusted side as well. So there is a lot of isolation in place, hardware-based isolation. So in order to do something really useful, we would like our TA that we have installed to have the capability of decrypting communication that is meant for other TAs in the system. So we needed to chain up other exploits with the fault injection in order to achieve that. So first comes the redirection part, by which I mean communication is meant for some other TA in the system, but we are redirecting that to ourselves. So we studied the communication protocol of Opti, and the way it works is the insecure world or the normal world. It invokes the services of the secure world through a unique identifier table, essentially. So all the TAs in the secure world, they have a unique identifier, and the normal world essentially provides that identifier to the monitor, and the monitor simply chooses that particular TA to execute, and a secure trusted application executes. Now in the global platform API specification, which is followed by Opti, it offloads this responsibility of choosing the unique identifier to the to the original equipment manufacturer. Now I'm using OEM or unique equipment manufacturer, this phrase in a very loose term, by which I mean when I say OEM, I mean the vendor like Linaro, which is working with Opti, plus the deployment. So whatever business is deploying Linaro's Opti in their business context. So I mean OEM as a combination of these two entities. The reason being, Linaro is contributing, for example, the kernel on the trusted side, the monitor code itself, And the business which is deploying arm trust zone, it is contributing its own code, the TA itself. So, and that can be anything. That can be some crypto thing. It can be a machine learning as a service on the machine learning on the edge, federated learning. It can be a lot of different contexts based on the business itself. So when I say original equipment manufacturer, I mean a combination of the vendor and the business that is deploying the product. And the specification says it's the responsibility of these entities to decide the identifier and ensure that no two identifiers collide. And this is a decent assumption because the very foundation of this API specification is that no other code other than obviously the business which is deploying can execute in the trusted part. So if no other code can execute, then we can safely offload the responsibility of choosing the identifier of those particular applications to the business, because no other code other than the business context is actually running in there. So it's completely fine assumption to break, to make actually. But what we found out was, in light of the fault attack we are proposing, we can now have arbitrary code execution on the TE side. And because we can have that, we can also choose the identifier of the code that we are installing in the TE side. And since we are the adversary, we can choose the identifiers to collide with the identifiers of already existing TAs. So essentially, the behavior of the system when non-unique UUIDs are used, it's undefined. It's not defined by the spec. So the empirical conclusion from our observations was that Opti is preferring a non-persistent TA over a persistent TA when there is a collision of identifiers. So persistence here is similar to how we define persistence for servers. So the idea is a non-persistent TA will destroy its resources like memory, the memory space that it has captured, or any peripherals that is communicating to after the session ends. A persistent TA will remain waiting for new connections from the normal world to come across. So persistence is like how we define persistence of servers, for example, like a keep alive persistence. And that's a redirection essentially. So if we install a non-persistent TA with UUID confusion, by which I mean the TA that we have installed will collide its identifier to match with a persistent TA, then the communication, instead of going to the actual TA, comes to the code that we have installed in the trusted part. But I have mentioned here as well, and recall that this communication is still encrypted. So even though we have been able to redirect it, it's still encrypted. So we still have to steal the session keys of the persistent TA in order to actually decrypt this. So that becomes the last exploit that we do. So the session keys for securing communication between the TA and the insecure world, it's based on symmetric primitives. And there exist third-party extensions which do a lot of elaborate key request, key transfer, and key surrender kind of mechanism, and several protections like blocking SIG trap. So SIG trap is a signal that is usually emitted by debuggers, and it also does a lot of other things like it blocks unauthorized reads to sensitive data pages. So essentially, there are mechanisms in place which protect the symmetric keys which are used to encrypt the communication that is going between the two worlds. And if I just summarize the timeline here, at some point, the innocent CA, so innocent CA, imagine that's on the red box, it is making a key request to this green box. That's the trust boundary, the key management module in the kernel. The module is transferring the key to the CA for its operation. And while the key transfer, or I should say after the key transfer and before the key surrender, the, the management module is doing a lot of other activities to make sure that the keys don't leak. And at a certain point, when the CA at a certain point when the CA is done with its task, it will simply surrender those keys back to the management module. And after that, it can have whatever communication it encrypted with the secure world. But what we found out was that this extension does not prevent segmentation faults or 6F signals to be raised against that CA. And that is again very intuitive because segmentation faults are usually raised in code when it tries to access memory address spaces which is outside its permissible limits. And the assumption is that the CA will not do it itself. So it will not deliberately jeopardize its own memory accesses. But because of the address bus faults, so if you recall, we had a data bus fault and we had an address bus fault. So we were able to inject segmentation faults as well when we did the fault attack. It's actually possible for us to do a segmentation fault after the key transfer has completed and before the key surrender occurs. This is happening on the normal world side. And once that happens, the entire key can be obtained from a core dump. And this is a completely valid trust assumption because the idea is on the normal world side, the adversary has complete control over the configuration of the kernel. In our experiments, we actually found that the default configuration of the opti kernel on the untrusted part actually had codumps enabled by default. But even if somebody switches it off, the threat model is completely permissible. We can switch those codums on, those codums back on the normal world side and mount this attack to actually extract the keys. And these are symmetric keys. So if we leak the key on the normal world side, the secure world side keys are automatically leaked because there's the session key. Had this been asymmetric primitives, then we would have had a much harder time. But since this particular extension was using symmetric primitives, leaking the key on the normal world side just simply broke down security of the secure world side. And here's a very simple summary of all the three attacks that I just mentioned. So assume there's a TA and is doing some machine learning on the edge on the secure world side. So the first attack is installing our own code, malicious TA. So the malicious TA with UUID X. So this UUID X is because I want to collide this UUID with the UID of something called a gatekeeper. I'm skipping why we chose the gatekeeper to attack, but the idea is there is a UUID match happening. And using false on the signature verification as we just discussed, the first stage ends up loading the code in the secure world. The attack 2 is the UID confusion part. So the TA that we are loading, we deliberately make it non-persistent. The gatekeeper which we are trying to replace, that is actually a persistent TA. So any CA in the system, any client application in the system that is completely innocent, it wants to communicate with the gatekeeper. That's the intended path, but it ends up communicating with the code that we have installed. And after that, the third portion of the attack, it will have 6F signals through EM faults again on the CA. So through EM faults, through address bus faults, we'll again inject or we'll force this particular binary into a segmentation fault. And through its codum, we'll have both the encryption keys and the signing keys, which essentially the CA has been given. So mostly it will have encryption keys. I don't think it will have signing keys. And even if it has signing keys, it will mostly be asymmetric. So it may not be of much value to us, but encryption keys are what we are looking for mostly. And then essentially, once we have all the keys with us, so we can decrypt communication for any other TA in the system. We can change it. Since we have the re-encryption, we can re-encrypt and re-encrypt it as well. And then if you want, we can re-sign it as well. But we essentially we were happy with decryption as well because we were happy with just uh, reading the messages which were meant for other TAs in the system. But you could, in principle, do a masquerading attack. So you could actually do a adversary in the middle attack essentially. So that's how all the three stages of our attack vectors they chain together to have an end-to-end exploit on OpT essentially. We did get a CV for this, and we worked together with Lenaro to deploy a countermeasure. Initially, Lenaro was of the opinion that we should be looking it from the specification point of view, but finally, after discussions, we ended up going with the redundancy based countermeasure. That's a very normal countermeasure against fault attacks. So the idea is we do the same operation multiple times. They were of the opinion that we don't need to fix the UID confusion problem if we stop the first attack vector here. So if we do the signature multiple times, we are inviting the adversary to fault all of those signature verifications simultaneously and correctly at the same time. And that's a much harder problem. It's not impossible, it's infeasible. And if we had stopped the first attack, then there's no reason why we should be ending up solving the UID confusion problem, because this is a harder problem to solve. This would have required many modifications to their own code base. So, and that's pretty much it. This was the setup, by the way, that we used. You could potentially do it with a much cheaper setup and a much lightweight setup like a chip shouter setup as well. Uh, and Yeah, so that's pretty much it. So thank you, and if there are any questions, then I'll be happy to answer.
Thanks, Nimis. So
Thank you.
I have a quick query. So you started your talk with the load instruction and then you injected a fault there, right?
Yes, yes.
Did you try with the stores?
We, yeah, we did try with the stores. We did not add it to the final paper, I would mean, because they were not of much interest to us, essentially. Like, we did not figure out what to do, but the store instructions were also vulnerable. Essentially, the memory cycles are vulnerable, so the stores are also vulnerable. The stores will have a lot of address space faults, the address bus faults, because most of the times we'll end up faulting the address of the store. But in some cases, we were able to fault the operand to the store as well. Yeah.
So if I understand correctly, I think if you mount a fault on a store, it is much more vulnerable, right? If you fault the data, that will now go to DRAM and that will become a permanent fault, right? Faulty data in the DRAM.
Yes, it will be faulty in the DRAM until it is refreshed by the program.
Yeah,
So
yeah,
like
yeah, yeah.
it will
But
be
you have that
faulty.
window,
It will
right?
be
You have
faulty.
that
We
window
have that
where.
window. Yeah,
Uh-huh.
we
So
have
I'm
that
just
window.
curious, did you see that? Were you able to do that? Okay.
Yes, as we were able to do that. There was no meaningful exploit out of it, but yes, we were able to do that.
Okay.
Thanks.
Hi, Nimish. This is
Hi. Hi.
Shantip.
Yes. Yes.
So, I have a question. So, regarding the final exploit that you showed, right?
Yeah.
So, in that case, I mean, this fault injection, you need to do two fault injection, but they are not like dependent on each other. So, first you do this TA insertion, and then at some later point, you need to do the other injection, right?
Yes.
So,
Yes.
the question is that, like, since you are injecting it, I mean, inserting a malicious TA in one of the, I mean, executions, if I understand correctly, on one of the parties, and
Right.
then this party is basically trying to send your keys outside, right? So is it, I mean, I was just wondering, like, this mechanism that you showed, that the keys are sent outside for some time, and then you fault and do a code dump and extract the key. Is it only possible? Yeah, this model is only possible because you have a malicious TA inside, or it is like a general model that they follow?
This is a general model, and this would work even if we don't have the TA inside.
Okay,
This is
so
independent.
then the attack model that the attack that you are showing in the next slide, can't it be simplified? Like I don't insert a malicious TA inside at all, but rather I just try the application which is sending the key outside. I just do a code dump, get the key, and then and it's basically one-to-one communication, and then I simply merge with it and just start communicating with the other TA, right?
You can do that. Okay, so if I if I if I just explain the architecture a little bit more, which I actually skipped because of time constraint. The reason we targeted a gatekeeper here as well, a
Mm.
gatekeeper here, was because this particular TA, it comes from Linaro, and it sits at essentially the gate between the two worlds, and then there are multiple TAs. So essentially, all communication to the your all communication to the secure world is essentially flowing through this TA. So
Okay.
any communication that is coming back,
Mm.
I would think I would think it would be possible to do. Yes, you're right in mentioning it would be possible to do by just the third exploit. It would be
Yeah,
possible.
because the third exploit, in my view, it's much easier because
Much easier.
you
Yeah.
can actually inject any random fault, and I mean most of the cases, and many cases, that might go create a bad address and code dump, and then you can recover the key from there much easier, right? With the first fault, you need to do a very precise timing, as it seems.
Yes. That is true. So it really, I would say, it depends on the context. So, for example, if you just want to know what the communication is happening between a CA and, let's say, this machine learning at the edge service, then just the third fault would work. If you would like to modify that, so for modify I mean, so CA is requesting an inference, for example, but you'd like to maliciously modify that inference. In that case, you'll have to replace the TA on the secure world side as well. So it really depends on the adversarial codes, I would say.
Yeah, and I was wondering, like this, once you can install the Gatekeeper TA, it can
Yeah,
be, I mean, it can result in even more powerful attack, because the Gatekeeper TA is basically keeping track of who is entering, who is communicating, everything, right? It's like a
yeah,
monitor. So
correct.
in that case, if you have a corrupted monitor, then typically you should be able to do much more thing, like, isn't it?
Yes, I mean,
I mean, you do not
yeah.
require probably the second fault at all. I mean, you are saying that you don't require the first fault at all. That I agree. But I was just thinking, if you can write down a malicious TA, and you replace the malicious TA with something, then why can't you do anything like you deliberately expose all the keys that these people are doing directly to the normal world? Because malicious TA can do that, right?
So the gatekeeper TA will not have the keys of the other TAs. It's acting like a router actually. It's acting like a router, but it's not playing any role in encrypting the traffic that is going through it. It's just like it's receiving a traffic and just deciding where that traffic should go. So I would say you're right. We can do away with either of the two faults, but that depends on the adversarial
Yeah,
context. Like,
yeah.
for example, if I just want to know what the communication is, then the third fault alone will do it. If I just want to do, let's say, a denial of service, I just want to make sure that nothing goes through to the secure world, just the first fault will be fine.
Yeah.
If you want to masquerade, if you want to masquerade, then both the faults will be needed, because now you do not just need to know what is being communicated, you also want the capability of changing it as well. So that's where the replacement part would actually come in. So it depends on the adversarial context, I agree.
Yeah, yeah. But yeah, it's pretty interesting to see. Another final question is that you are using that pattern triggering, I guess, right? I mean, which
Yeah.
oscilloscope you are using in the lab? The new ones or the old one?
So when this when this happened, I was using the old ones you see here. That's the old ones, but
Yeah, this was a broken one, I remember. The
yeah,
Oprios.
that's the
Yeah,
old
it
one.
was
But
broken ones. But yeah, so the serious question is that at what frequency the pi was working, because this doesn't have a great bandwidth, I suppose, right?
yes, that's a very good question. So the pi we were working with, it has like goes from zero point 0.8 gigs to 3.2 or 3.4 gigahertz.
Hmm.
So the frequency of the core could be controlled using CPU power utilities on the normal world side. That's the untrusted part. So we fixed it at the minimum possible. because that gives
Yeah,
us
that's a judicious, yeah, and sampling frequency of this one, I think 2.5 gig, right? Gig sample, this one, or even lesser, I guess.
even lesser. Yeah, even lesser.
Yeah, it's
So
even lesser. So you are using the pattern trigger from the backside, right? I guess. Yeah.
yes.
Okay. It's good to see that it works. The old one also works. Cheaper ones, yeah.
Yeah.
Yeah. Great. Thank you,
Thanks.
Nimish. Thank you.
Thank you. Thank you.
Mhm.
Okay, I think in the interest of time, I have to stop. I have a meeting at 4. But great talk.
Thank you. Thank you for having me here again. Thank you.
Yeah, let me stop the recording.